Let's look at some examples. This is the example we started to look at before, the alternating harmonic series. This is just 1 minus a half plus a third minus 1/4 plus 1/5 minus 1/6, etc. Does the series converge? Well, I'll refer to the alternating series test as the AST. The alternating series test tells us this converges, since what we call b sub n here, that's just the 1 over n part, the sequence b sub n is decreasing. It's clear that the bigger n gets, the smaller 1 over n gets. And the limit as n goes to infinity of b sub n, that's just the limit as n goes to infinity of 1 over n, that's clearly 0. So the alternating series test tells us immediately that that series converges. What if we want to estimate the sum? Well, I said we'll learn how to understand the exact sum for this particular series much later, several sections from now. But if we want to approximate the sum, we can say that the sum is just approximated by a partial sum. And let's look at S sub 5, for example. S sub 5 is just 1 minus a half plus 1/3 minus 1/4 plus 1/5. You could easily add these together and write that as a single rational number or get a decimal approximation. That's some number. How close is that to the actual sum S? If I said, here's my approximation, I'm just going to use this instead of the actual value of the series S. How wrong am I? Well, the size of the error, that should be R5 here, the size of R5 here is smaller than the magnitude of the next term, which is 1/6. So if you get a decimal approximation for this, you know that you could be off by as much as 0.16666, etc. So that's pretty close. But what if you need to know the answer to 3 decimal places? Or let's just say you need to know the answer to within 0.001. Will this partial sum be close enough? Certainly not. The error, we can tell, is at most 1/6. That's not good enough to be sure that we're within 0.001. How can we be sure we get to within 0.001? Well, we can use S sub 1000, which is 1 minus a half plus 1/3 minus 1/4. And we keep going here all the way to plus 1 over 999 minus 1 over 1000. That's the 1000th partial sum. Now, it would be hard to compute that by hand, but with a calculator or a simple computer program, that's a triviality to compute. And what is the error? R sub 1000. Well, the size of that is less than the next term, which would be 1 over 1001, which is less than 0.001. So we know that if we compute S sub 1000, the 1000th partial sum, we get close to the actual answer. How close? Definitely within 0.001. Let's look at a different example. Let's say we have this series, the sum. I'm starting here from n equals 2 just because this formula wouldn't be defined when n equals 1. So I'm going to take the sum from 2 to infinity, and I'm going to write minus 1 to the end just so that the first term, that's the term with n equals 2, is positive. There's no reason you have to do that. Everything works the same if you start with the negative term. But now I can just write that this sum is 1 over log 2 minus 1 over log 3 plus 1 over log 4 minus 1 over log 5, etc. Now, does this series converge? The alternating series test tells us this converges. Why? Because these terms, b sub n, which is 1 over log n, they're certainly decreasing and have limit 0. They're decreasing because the bigger n is, the bigger log n is. The natural log function is increasing, so log n gets bigger when n gets bigger, and thus its reciprocal gets smaller. And we know that since log n actually tends to infinity, it blows up, the terms get arbitrarily large. 1 over log n tends to 0. Now this log n grows much more slowly than n, so 1 over log n actually tends to 0 much more slowly than 1 over n does. And yet the alternating series test doesn't care about how slowly the sequence tends to 0, just that it tends to 0, and so this sequence converges. There's no nice formula for the exact value of this sequence, but just using my computer, I computed the sum from n equals 2 to infinity of, say, minus 1 to the n times 1 over log n is approximately 0.92. If you compute these and go out a very, very, very long way, you get an answer that's approximately 0.92. Here's a question. How close would we be if we took the sum from, say, if we took the sum from n equals 2 to 8? In other words, we took s sub 8. It would actually maybe even be s sub 7 because we're starting with 2. I'll still just use s sub 8, and I'll call that 1 over log 2 minus 1 over log 3 plus 1 over log 4 minus 1 over log 5 plus 1 over log 6 minus 1 over log 7 plus 1 over log 8. How close is that to the actual sum s, which is about 0.92? Well, the size of the error, size of R8, would be less than the size of the next term, which is 1 over log 9. Well, how big is log 9? Log 9 is only a little bit bigger than 2, because remember, 9 is only a little bit bigger than e squared. So this is only a little bit less than 1/2. It's less than 1/2, but not much less than 1/2. So we can say the error will be less than 1/2, which is still pretty far off using these 8 terms. What if I need the error less than 0.001 again, like for the last series that we were talking about? Well, then let's use this formula. The size of Rn will be less than 1 over log n, and we would need 1 over log n to be less than 0.001, which means n, if I flip this upside down, log n has to be greater than 1,000, or n has to be greater than e to the 1,000th. Now, e to the 1,000th is an astonishingly huge number. 1,000 is pretty big, but e to the 1,000 is just ridiculously big. And you'd have to go all the way out to the e to 1,000 to the 1,000th term to know that you had the value of the e to the 1,000th partial sum within 0.001 of the correct sum s. That's an astonishing amount of computation. You couldn't compute that exactly with any computer. And that's just to get a 3 decimal place approximation for s. Now, there are other things you could do to get a good approximation for s, perhaps, but just using partial sums, you'd have to compute so far out, it's ridiculous. Why? It's because this sequence tends to 0 very slowly. Log n gets big very slowly as n gets big. When n is up to e to the 1,000th, log n is only about 1,000, so 1 over log n is around 1 over 1,000. In fact, exactly 1 over 1,000. So even when you go out to e to the 1,000 terms, which is astonishingly far out, the size of the individual terms is still about 1/1000th. And that's why it just takes such a long time for this series to converge, though it does converge to a finite value, in fact to about 0.92. Finally, let's take a look at this series. Remember, we showed with the integral test that the sum, even the sum of 1 over n squared, n equals 1 to infinity, this is 1 plus a fourth plus a ninth, etc., converges. And I told you that it takes some more complicated methods to show this. We won't even be able to get to show this in this course. But one can show, Euler showed this, that the value of this series is pi squared over 6. A very strange number, a beautiful number in mathematics. What about the alternating series whose terms are the size of 1 over n squared? So this alternating series looks like 1 minus 1/4 plus 1/9 minus 1/16 plus 1 over 25 minus etc. Does this converge? Well, immediately we see the alternating series test tells us the series converges, since the b sub n's, the magnitudes of the terms, are decreasing and have limit 0. Let's say I want to approximate the value what I'll call S, the total sum of this series. If I want to approximate S to within, let me just use 0.01 here, to 1/100th, how many terms do I need? Well, if I use n terms to compute S sub n, the error, which we call R sub n, is at most the next size of the next term, which is 1 over n plus 1 squared. So if I need the error R sub n, the size of the error, to be less than 1 over 100, I need n to be at least 99, because then this will be 1 over, not 99, totally wrong, 9, because then this will be 10 squared in the denominator, and this will be 1 over 100. So S sub 9, which is exactly, that should be a 9, which is exactly 1 minus a fourth plus 1/9 minus 1/16 plus 1/25 minus 1/36 plus 1/49 minus 1/64 plus 1/81. This isn't exactly the full sum, but this is correct. That means as an approximation for the full sum S, for the full sum S, to within 1 over 100 or 0.01, just the sum of these 9 terms. And here's another really neat fact, which again we won't be able to show this quarter because it takes some more advanced methods, but this full sum is actually exactly equal to pi squared over 12. Surprisingly, exactly half of this full sum.